Welcome to Introduction to Composites. Today is the 5th day of the ongoing week, and today and tomorrow we will introduce and discuss a new topic in detail, and that is about how to predict whether a single layer of composite which is loaded in a plane stress state, how can we predict its failure. So, our theme of discussion is failure theories, for especially orthotropic lamina, and since it is very thin, we assume that it is plane stress, that is assumed. Okay. So, before we start discussing in detail, we know based on our earlier studies that if we have to predict failure in case of metals which are isotropic materials, then we have several theories of failure. For instance, maximum stress theory, another one is maximum strain theory, another one is maximum strain energy theory, then there is another one known as von Mises theory. And in several of these theories we use the concept of principal stress, and we compare the value of principal stress. So, what we do is we compute the value of principal stress and we compare that value with the failure strength or with the strength of the material, and if the strength of the material is more, then we say the material is not failing. If the strength is less compared to principal stress or principal strain, then we say that the thing is failing. So, this is what is done at least in context of isotropic materials, and the reason we are able to do this in case of isotropic materials is because the strength of the material is same in all directions. So, it does not matter whether you pull a rod, if you have a piece of metal and you pull it in x direction or y direction or z direction, its strength does not change with respect to the orientation of the force, its strength remains the same because it is an isotropic material. So, when we compute the principal stress, the principal stress is associated with a particular direction, it could be anything, but in every direction, because the strength is same, I can compare that principal stress with the strength, and because the stress is same, I can compare and see whether the thing is going to fail or not. The same cannot be said in case of composites, and the reason is I can still compute principal stress, which will be the direction which will experience highest stress, but the strength of the material keeps on changing. So, for different directions it has different strengths. So, I cannot compare the principal stress with a particular number which exists in case of isotropic materials. So, because of this fundamental problem, we cannot use any failure theory which is used in isotropic materials as is and to predict the failure of composites, or in this case especially orthotropic lamina. So, this is the background. So, we have to develop a different framework of predicting how do composites and especially orthotropic lamina loaded under plane stress fail. So, in that context, first thing what we will do is we will say that the especially orthotropic lamina under plane stress has 5 important failure properties. So, first thing is 5 failure related material properties. 5. So, these are 5 fundamental failure material related properties. What are these? The first one is sigma Lu, and in this case this is the ultimate tensile strength. So, U is ultimate. sigma Lu tensile strength in L direction. This is the first fundamental. The second one is sigma Lu prime. So, here it is, if I have a lamina and if I, instead of pulling it in tension, I compress it, it may fail also at some load. So, this is ultimate compressive strength in L direction. Okay. So, these are two properties. Similarly, we have two properties for transverse direction. Sigma Tu is ultimate tensile strength in T direction, transverse direction. And then we have, so what is sigma Tu? It is, fibers are like this and I am pushing it, I am pulling it in tensile direction, but in the transverse direction. And sigma Tu prime, here the prime indicates the direction is compressive, it is ultimate compressive strength in T direction. And the last one is tau Ltu, it is ultimate shear strength, corresponding to LT plane, So, what that means is the lamina is loaded only under shear and it may fail and the fibers are like this. Okay. So, these are 5 material related properties associated with failure of a thin lamina, especially orthotropic lamina, which is subjected to a plane stress situation. Now, using these 5 properties, 3 theories will be discussed, which will help us understand when a composite is going to fail. The first one is maximum stress theory. Maximum stress theory. So, what does this theory say? That if, so the material, so a single lamina is not going to fail as long as the stresses in the LT and LT direction, sigma L, sigma T, sigma tau LT, as long as they are less than their respective strengths, then the thing is not going to fail. If any one of those stresses exceeds one of these things, then the material is going to fail. So, mathematically, what does that mean? That for no failure, the following conditions have to hold true. Sigma L should be less than sigma Lu, sigma T should be less than sigma Tu, and tau Lt should be less than tau Ltu. Okay. All of them have to hold simultaneously. Now, there could be a case that sigma L is negative, then in that case the condition would be sigma L should be less than sigma Lu prime, and if sigma T is less than negative, then sigma T should be less than sigma Tu prime. So, it depends. If sigma is compressive, then you have to compare it with its compressive strength in the L or in the appropriate direction. Okay. So, these 5 conditions are there, and as long as all these 5 conditions are true, even if one of the condition gets violated, then the material is going to fail. So, this is the first theory for failure of composite materials. Okay. So, let us do an example. . So, the example is we have a lamina and I am applying some stresses on it. So, what are the stresses? 50 MPa in tension. These are my direction of fibers. So, this is my L direction, this is my T direction, this is my X, this is my Y. So, in the Y direction, the stress is negative. So, it is minus 25, and then I have also a shear stress applied, and the value of shear stress is 50. So, all these are MPa. So, tensile stress in x direction 50 MPa, compressive stress in y direction 25 MPa, shear stress 50 MPa, and the material properties are also given. So, let us see what the material properties are: sigma Lu, sigma Lu prime, sigma Tu, sigma Tu prime, and tau Ltu. So, this is all given. So, what are their values? This is 1062, this is 31, this is 72, this is 610, and this is 118. Okay. So, these are all in MPa. So, the question is, will the material fail? That is the question. So, what do we do? First, we compute sigma L, sigma T, and tau Lt. Okay. So, we compute sigma L, sigma T, tau Lt, and what is this? This is nothing but that transformation matrix T1 times sigma x, sigma y, tau xy, and we know how to calculate this transformation matrix. We know it. So, we do all these calculations and we find that these values are 37, minus 12, and 57.4. So, these are the values. So, sigma L is equal to 37, sigma T is minus 12.1, and the shear stress tau Lt is 57. So, now we compare whether any of these values is exceeding its limit. So, first we see 37 and we compare it with 1062. So, it is not exceeding. So, this is okay. The second number is 12.1, but it is negative. It is 12.1, but it is negative. So, we compare minus 12.1 with 610, and again it is not failing. The third one is 57.4, and we compared with the shear strength of the material, and again it is not exceeding. So, all the conditions are met. So, no failure. Okay. There will not be any failure. So, this is the way to do this. So, this is how the maximum stress theory works. Okay. The next theory we are going to look at is maximum strain theory. Maximum strain theory. So, in stress theory we had 5 fundamental properties related to these are the 5 properties which are important, and here we are saying that the material will fail at a certain stress state. In strain theories we replace these 5 material properties by similar material properties, but strain related. So, ultimate tensile strain in the L direction will be epsilon Lu, ultimate compressive strain in L direction will be epsilon Lu prime, and so on and so forth. The maximum strain theory says that the failure will not happen if all of following hold true. What are the following conditions? Epsilon should less be epsilon LU, epsilon T should be less than epsilon TU, and gamma LT should be less than gamma LTU. And suppose instead of tensile stress, tensile strain, I have a compressive strain, then we look at epsilon L should be less than epsilon LU prime, and epsilon T should be less than epsilon TU prime. So, these are the 5 conditions. Okay. So, these conditions, as long as they are valid, the material does not fail. If any one of them gets violated, they fail right away. Okay. Now, we will connect this theory with the maximum stress theory for linear elastic materials. For linear elastic materials. For linear elastic material, what does that mean? What that means is that if I keep on pulling the material, if I double the stress, the strain also doubles. Okay. So, in that case, if I have a stress strain response, so here I am having strain and here I am having stress, it is a straight line. It is not a line something like this. This is not the response. If it is this kind of a line, then I can say that epsilon LU, epsilon LU is what? It is equal to sigma LU by EL, only if the line is straight. If it is not straight, then I cannot have this. Similarly, epsilon TU is equal to sigma TU divided by ET, right. Tau LTU is gamma LTU is equal to tau LTU divided by G LT. Epsilon LU prime is equal to sigma LU prime divided by EL, and epsilon TU prime is equal to sigma TU prime divided by ET. Okay. So, for linear elastic materials, the prediction from maximum stress theory and maximum strain theory are very close to each other. There is slight difference because of effects of Poisson ratios, but otherwise they are fairly close to each other. Maximum stress theory and maximum strain theory give you the more or less the same results. But if the material is not linearly elastic, for instance the matrix is plastic and it just deforms heavily before failing, suppose, or if the fibers initially they may be elastic, but later say suppose they turn plastic before failing, then the material will not be linearly elastic. In that case, we cannot use these types of relations. We can still use these relations, but these relations, the second set of relations cannot be used. So, for linear elastic materials, the predictions from maximum stress theory and maximum strain theory, they come pretty close to each other. So, this is the second theory which has been talked about, and the final theory is known as, which we will discuss today, and this is the most popular one, is known as maximum work theory. And it is also known as Tsai-Hill theory. Tsai-Hill theory. So, here it is related to the work done by the system, strain energy and things like that, and we are just directly going to share you with tell you the results. So, what does the result say? It says that the system is going to fail if the right hand side of this equation exceeds 1. If it does not exceed 1, then it will not fail. So, what is this? Sigma L divided by sigma Lu square minus sigma L divided by sigma Lu times sigma T, and remember here the denominator is still sigma Lu, not Tu, I am sorry, the sigma Lu plus sigma T divided by sigma Tu whole square plus tau Lt divided by tau Ltu whole square should be less than 1. So, for no failure. So, here a good thing about this is that you do not have to have 5 different conditions. One equation will tell you whether the thing is going to fail or not, right. In other maximum stress and maximum theories, you have 5 different equations, and you have to make sure that each of them is not being violated. Now, here I wanted to make some things clear. Here, if sigma L is negative, then we have to consider, if sigma L is compressive, then we have to consider sigma Lu prime. Okay. So, we have to modify this thing. Similarly, if sigma T is compressive, then we have to consider sigma Tu prime. Okay. So, this could be sigma Lu or sigma Lu prime. This could be sigma Tu or sigma Tu prime, and same thing here, sigma Lu or sigma Lu prime. And there is a special situation in this case. What is that? That if sigma T is positive, then we consider sigma Lu. And if sigma T is negative, then we use sigma Lu prime. Okay. This is important to understand, otherwise we may get confused and we may use wrong numbers. Okay. So, based on this we can calculate whether the right hand the left hand side of the system is less than 1 or more than 1. If it equals 1 or if it is more than 1, then there will be failure. If it is less than 1, then we are okay. Now, a special case could be for uniaxial specimen. What does that mean? That it could be something like this. So, here I am having loading just in the x direction, sigma x, sigma y, tau x y, suppose they are all 0. So, this is theta. Okay. Then if this is the case, then I can say for this kind of a situation, I can say that sigma L, again using our matrix of T1, sigma L is equal to sigma x cosine square theta, sigma T is sigma x sine square theta, and tau Lt is equal to sigma x sine square theta cosine square theta. I am sorry, it is just sine theta and cosine theta, I am sorry. So, if we are applying only sigma x, then these are the values of sigma L, sigma T and tau Lt. And if that is the case, then I can put, let us say this is equation number 2 and let us call this equation number 1. then I can put 2 in 1 and what I get is cosine 4 theta by sigma Lu prime sigma Lu square minus cosine square theta sin square theta by sigma Lu square plus sin 4 theta divided by sigma Tu square plus sin square theta cosine square theta by tau LTU square is less than equal to 1 over sigma x square. So, this is the equation for a uniaxially loaded specimen. Okay. So, sigma x, sigma y, tau x y are 0, right. So, it is minus of that thing, yes. So, this is negative of it, but then it gets squared. So, it gets corrected. Okay. Okay. So, this is the maximum I mean the Tsai-Hill criteria for predicting failure. So, what we will do is we will again check on this example, this example, and see whether the Tsai-Hill criteria tells whether this thing is going to fail or not. Okay. So, we will again redo this example. So, sigma x in this case is 50, sigma y in this case is minus 25, tau xy in this case is positive, and it is important to remember the signs of stresses, and that is something we will discuss later also. So, minus plus 50, and then finally sigma Lu equals 1062, sigma Tu equals 31, tau LTU equals 72, sigma Lu prime equals 610, and sigma Tu prime equals 118. So, we have already calculated all the values. So, sigma L we calculated earlier, and theta we had defined was 60 degrees. So, for this sigma L we calculated as 37, sigma T as minus 12.1, and tau LT as 57.4. Okay. Now, with this condition, let us apply the Tsai-Hill criteria. So, here we have 37 divided by this 37. So, this is, and this has to be divided by Lu 1062, the whole thing square, minus 37 divided by 1062 times the second thing. So, what is the second term? Sigma T divided by sigma Lu. Okay. Now, here, so sigma T is minus 12, sigma T is minus 12. So, of course, we just take the number, we do not use the, so it is 12.1, and we divide it by, because this is compressive, so we consider 610. Okay. So, this is 610, and then of course, the third term is 12.1 divided by 118, because the third term says sigma T divided by sigma Tu. So, sigma T is negative 12.1. So, we consider sigma Tu prime, which is 118. So, this is square, and then finally, we have the shear thing 57.4 divided by 72, and this works out to be 0.6, which is less than 1. So, the material is safe and will not fail. So, this concludes our discussion for today. We will close this discussion tomorrow by discussing some more finer aspects of this theory, and specifically we will discuss the direction of shear stresses in this context, and that will close the discussion for this week and also the theme of this week's topics. So, with that wish you the best of evening, look forward to seeing you tomorrow. Bye.